Equipment. In this module, you will examine items of equipment suitable for deep diving, further your knowledge about regulators, and find out how to use a decompression bar and a John line. Diving equipment for deep diving. In order to make a deep dive, the equipment must be suitable for the new demands. The equipment you already have is probably suitable, but you must make sure that it is. On a deep dive, you could go beyond the thermocline, which is the surface of separation between two layers of water of different temperatures. So this means that the suit you use must be suitable for the water temperature at the bottom, not at the surface. What is more, at depth, a wetsuit is subject to greater compression and loses not only its buoyancy but also some of its insulating power. On deep dives, in cold water, the use of a dry suit could be a good solution. In this case, it is advisable to do some special training like that offered on the PSS dry suit diving course. At depth, the greater reduction in the volume of the compressible equipment produces a reduction in the lift, which must be compensated for by putting a greater quantity of gas in the buoyancy compensator. This is why it is necessary to use a buoyancy compensator with an air bladder large enough to compensate for the greater weight. At depth, the consumption of breathing gas increases, so the cylinder capacity must be sufficient to guarantee suitable autonomy and a wide safety margin. A 15-litre cylinder is usually an ideal compromise. A DIN fitting is recommended because it provides a more reliable connection between the regulator and the cylinder valve, as the O-ring seal is completely enclosed. The pressure gauge is an essential instrument for measuring consumption. On a deep dive, this instrument must be checked frequently to prevent the risk of running out of the breathing mix. The techniques of navigating underwater using a compass are part of the compulsory training on the PSS Advanced Open Water Dive course. However, due to the importance of these skills on deep dives, you will practice using a compass for navigating at greater depths on the third dive of the PSS Deep Diver course. On deep dives, you must also use a dive light, which for this type of activity becomes necessary. In fact, using a dive light is the only way to compensate for the selective absorption of colors and the reduction of natural light. Lastly, the use of a dive computer is compulsory on the PSS Deep Diver course. The depth itself is a penalizing factor regarding the dive time. A dive computer allows you to make longer dives within the no-deco dive time than if you made the same dive using the dive tables. This is particularly true when making repetitive dives. Regulators. The purpose of a diving regulator is to reduce the high pressure of the breathing mix in the cylinder, variable with time, to ambient pressure, variable with depth. All dive regulators are open circuit, meaning that after taking a breath, the diver exhales the air into the surrounding water. Diving regulators are on demand, meaning that they supply breathing gas only after the diver has demanded it and adjust automatically to the changes in depth. The first models were single stage, meaning the change of pressure occurred in just one stage. technical evolution has led to the two-stage model, which is easier to breathe from as the final change in pressure occurs right in front of the lips. The function of the first stage of a two-stage regulator is to reduce the high pressure of the breathing mix in the cylinder to an intermediate pressure or hose pressure, which is equal to the ambient pressure plus a predetermined value. The second stage of a two-stage regulator further reduces the intermediate pressure to the ambient pressure so we can breathe effortlessly. The first stage. There are two types of first stages: diaphragm and piston. The main difference is that the pressure-reducing mechanism in the diaphragm type, contrary to the piston type, works in a dry environment. In the piston type first stage, the ambient pressure is transmitted to the pressure-reducing mechanism directly by the water that enters it. Instead, in the diaphragm type, the ambient pressure is transmitted via the force exerted on the diaphragm. This is why diaphragm-type first stages are preferable for dives where there is a lot of silt suspension in the water. The dirty water remains outside the pressure-reducing device and therefore cannot damage the mechanism or affect its working properly. Downstream and upstream valves. The passage of breathing mix from the first to the second stage of a regulator occurs through the opening of a valve. This valve can be either downstream or upstream, depending on the direction the valve opens in respect to the flow. A valve is downstream when it opens in the same direction as the flow. If the valve opens in the opposite direction to the flow, it is said to be upstream. The advantage of a downstream valve is that if the pressure upstream is higher than normal, the valve will open and allow gas to flow out. This is why all safety valves are of the downstream type. The disadvantage is that the force generated by the thrust of high pressure on the area of the valve head changes with the variation of pressure in the cylinder, thus affecting its performance. Balanced valves arise from this fact. Balanced valves. Upstream of every valve, there is an imbalance of forces due to the reduction of pressure as the diver consumes the breathing gas. Balanced valves were designed to reduce the effort of opening the valve, meaning in such a way so that the pressure acting on the valve head is counterbalanced by an identical force that acts in the opposite direction. A special balance chamber ensures that the same pressure that there is upstream of the valve acts on an area of the piston the same as that for the passage of the breathing mix. There are two ways of connecting the balance chamber: using an external or an internal feed line, which is usually the method used in regulators. In this way, with variations to the high pressure, the effort of opening remains practically the same and is dependent on a single spring. When the two areas on which the axial forces act are the same, the valve is perfectly balanced. If they are different, the effort of opening varies with the changes in pressure upstream. For example, if the head of the valve stem has a smaller area than that for the passage of the breathing gas, the valve is partially balanced. In the opposite situation, the valve is overbalanced, and the effort of opening is reduced as the pressure upstream fails. The second stage. In regards to how it functions, the second stage of the regulator is much less complex than the first stage. It is just a simple pressure regulator on demand, which functions with the difference in constant pressure, meaning that it brings the breathing mix from the intermediate pressure to the ambient pressure, making a change equal to a predetermined pressure. The heart of the second stage is the downstream valve. The seal of the downstream valve is created by a seal mounted on the piston, which is pushed by a spring against the seat. By breathing, we lower a membrane, which activates a lever which then pushes the piston away from the seat and allows the breathing gas to pass through. Once inhalation has stopped, the membrane returns in position and the spring pushes the piston back against the seat, closing the flow of breathing gas. Balanced valves can also be used in the second stage. Using a balanced valve means that the force of the spring can be greatly reduced, and consequently breathing requires less initial effort. As well as the balancing of the piston, with time a second stage with an adjustable flow, which acts on the compression of the spring, has also proven useful. If the calibration is optimal, on the surface the second stage of the regulator should go into free flow with the adjusting knob unscrewed, and stop when the knob is almost completely closed. In this way, as you descend, you can unscrew the knob and reduce inspiratory resistance to as little as possible. As you ascend, you can begin closing the knob to stop the tendency that the second stage has to free flow. We speak about initial respiratory force to indicate the effort needed to open the valve of the second stage. The subsequent force, inspiratory force, needed to keep the valve open is always less than the initial effort required, also due to the laminar airflow which opposes the closure of the piston. The fluid dynamic effect venturi, or a dragging or ejector effect, is much more effective. By directing the flow of air into the mouthpiece, we obtain downstream a pressure just a little greater than the ambient pressure, and upstream, in the casing of the second stage, a slight depression. This depression helps to keep the membrane lowered. In this way, the inspiratory effort can be reduced to zero. With some of the early Venturi models, any slight accidental maneuver was enough to trigger a free flow. To reduce this effect, manufacturers invented depression limiters, which introduced obstacles along the route of the gas flow. An alternative solution is to use an external bypass tube. In practice, the air passes from the second stage valve directly to the mouthpiece by means of a small auxiliary bypass tube, keeping the chamber of the second stage almost completely in depression and greatly reducing the respiratory effort. Still with the purpose of reducing the respiratory effort to the minimum, an element commonly used in mechanics has been applied to regulators: servo assistance, meaning a mechanism that is able to carry out a given function after receiving a particular command. With the servo-assisted second stage, the depression created by our inspiration uses the same air at intermediate pressure to open the valve. In simple terms, we can say that instead of opening the valve of the second stage, our initial respiratory effort serves to open a very small valve. In this way, the initial effort is reduced to as little as possible. Emergency air sources. One of the reasons why the buddy system is important is that it avoids having to carry around a reserve of breathing gas in case of an emergency. In case of problems, you can share your supply with your buddy. On the PSS Open Water Diver course, you learned that there are various types of emergency air sources. These may be dependent on your buddy, octopus system, or integrated into your BC, or completely independent, small auxiliary cylinder. A valid system when deep diving is a second regulator, completely separate from the main one. In this case, you will need a cylinder with a double outlet. The emergency regulator is mounted on the second outlet and is available for your buddy to use. The hose of this regulator should be long and possibly a color that is easily visible. When making a deep dive, an eventual emergency due to running out of breathing gas or a regulator failure is complicated by the fact of having to make the ascent from depth. The use of two independent regulators is far preferable to an octopus system, and in fact, some first stages may also have a reduced air flow capacity at depth and prove insufficient to allow two divers to breathe easily at the same time. The use of two independent regulators also allows you to manage a failure. For example, in the case of a free flow, it is enough to close the knob of the valve on which the malfunctioning regulator is mounted and breathe from the other one. The procedures for using emergency air sources are not, in fact, universally standardized, so when diving with a new dive buddy, it is important to identify the second stage and clearly establish how it should be used before beginning the dive. Support equipment. On deep dives, it is advisable to use some items of support equipment. We will begin with the shot line. This is a taut vertical line that goes from the surface to the seabed with a weight of around 5 to 6 kilograms, 10 to 13 pounds. The line should be of an adequate diameter, not too thin nor too thick, because although a thick line would make the descent and ascent more comfortable, it would also take up more space. The length of the line should be about 2 meters, 7 feet less than the depth, allowing the line to remain taut and prevent the weight at the bottom becoming entangled or damaging the seabed. A shot line allows the diver to reach the seabed easily and to keep a better check on the descent and ascent rate. Descending or ascending too quickly exposes a diver to the risk of embolism, AGE, or barotraumas. The shot line is useful for maintaining the correct rate. If you realize that you are going too fast, you can stop by just holding onto the line and adjusting your buoyancy. A shot line is also useful for maintaining contact with your buddy, reaching the seabed easily in low visibility, and avoiding disorientation on free descents and ascents in the blue. It also prevents divers being dragged away by strong currents and helps them maintain the correct depth for safety or emergency decompression stops. The anchor line or chain can be used for descents and ascents. However, this is not perpendicular to the seabed, so the descent and the ascent will not be vertical. Furthermore, rough seas could make an anchor line difficult to use because, due to the movement of the boat, the line tends to move up and down, making it more complicated to stay at the correct depth for emergency decompression or safety stops. However, the anchor line is useful in strong currents. In many situations, a John line is very useful for making a safety stop or an emergency decompression stop, as it eliminates the changes in depth caused by the oscillating movement of the boat. The John line allows the diver to make a safety stop some distance from the anchor line without being dragged away by the current, and is also useful when diving in a group, as there are fewer divers holding on to the shot line. Another important item of support equipment is a decompression bar. This is a weighted bar that is deployed from the boat and positioned at a depth of 5 meters, 15 feet. Its purpose is to give the divers a depth reference at which to make the safety or emergency decompression stop. Some weights fitted with a clip are also attached to the decompression bar, and these can be used by divers if they find they are positively buoyant. On deep dives, an emergency cylinder with a pressure gauge and at least 2 second stages is lowered over the side of the boat to a depth of 5 meters, 15 feet. It is generally attached to the decompression bar or to the shot line and available for anyone who needs it. The cylinder valves must be closed, but there should be pressure in the regulator. The cylinder must contain air if all the divers are using air. Instead, if the divers are using nitrox, the emergency cylinder must contain a nitrox mix with the same percentage of oxygen as the highest being used on the dive. This enables you to continue to use the data of your nitrox computer even if you used a mix with a lower percentage of oxygen. In the next module, you will learn how to calculate consumption and autonomy and how to breathe at depth. You will also learn more about hypercapnia and nitrogen narcosis and how to avoid and resolve it. See you soon.